Okay, let's dive right into this explainer. We've got to start by acknowledging a massive, honestly universal frustration for developers building generative AI coding tools. I mean, you're building these agentic systems, you connect all your tools, and then suddenly, boom, you're hit with failed tool calls, endless retries, and token costs that are literally through the roof. It leaves you wondering if the whole shebang was even worth building. Today, we're going to unpack exactly why that happens, and more importantly, how to engineer your way out of it.
So why do model context protocol tools underperform? Well, we need to shatter a common misconception right out of the gate. If your agent fails, it is almost never the protocol's fault. It's actually a flaw in the tool design itself. See, the classic developer move is to expose an existing API as it is, plug it in, and kind of just cross their fingers hoping the LLM figures it out. But for anything past a basic hello world, that raw pass-through approach is a guaranteed train wreck.
Here is our architectural blueprint for today. 1. Why MCP tools fail. 2. Bloat and confusion explained. 3. Leveling up, descriptions and schemas. 4. Advanced tactics, lazy loading. 5. The agent as tool approach. And 6. Trade-offs, choosing your path.
All right, section 1, why MCP tools fail, specifically looking at the anti-pattern of raw pass-through. Exposing existing APIs as is without designing for how large language models actually think is a huge anti-pattern. Let's use a simulated K-12 education content search API as an example. If you hand an LLM a raw database schema filled with internal jargon, it has absolutely no guidance. It's going to make wrong choices. It might guess a field expects the word quiz when your database literally requires the word assessment. Those wrong guesses trigger retries, and those retries just relentlessly chew through your valuable context window. Which brings us to section 2, bloat and confusion explained. These are really the twin villains of context engineering. What's absolutely fascinating here is that mastering context engineering is a constant tug of war between two opposing forces. On one side, we have bloat. This is when tool definitions load on every single call, taking up precious space. As that context fills up with massive, heavy definitions, the model's ability to reason effectively just degrades. On the flip side, we have confusion. Ambiguous tools cause poor choices, wrong parameters, and compounding retries. When an LLM gets confused, it acts like a frustrated assistant, blindly guessing, hitting empty no results errors, and eating up tokens, which ironically directly creates more bloat.
So let's talk about how to fix it in section 3. Leveling up, descriptions and schemas, walking through iterations 1 through 3 of our K-12 API.
Here is the evolution. Step 1 is that V1 raw pass-through, where it's all internal names and we're just hoping the LLM magically knows our conventions. It doesn't. Step 2, our V2, adds rich descriptions. We map out synonyms, so accuracy definitely improves, but we take a massive hit on bloat. The tool definition gets incredibly heavy. And then we arrive at step 3, V3, introducing schema constraints with enums and smart defaults.
Let's zoom in on what makes V3 a real game changer. Instead of writing massive paragraphs to explain clunky database columns, we just rename them. We change internal jargon like content_bucket to something beautifully LLM-friendly like resource_class. We set sensible common defaults. We constrain the options using enum schema types, meaning the schema itself strictly dictates what's valid, and we provide targeted error messages instead of empty results. By doing this, we drop the context size significantly because we've completely removed the guesswork for the LLM.
Moving on to section 4, advanced tactics, lazy loading, or on-demand context retrieval.
So what do you do when you have wildly complex schemas or tons of connected tools where even optimized descriptions cause bloat? You use lazy loading. This means removing those complex descriptions and massive enum lists from the always loaded context entirely. Instead, you provide a separate discovery or taxonomy tool for on-demand retrieval. You keep the main search tool lean, and the LLM only reaches for that taxonomy tool when it actually needs to look up valid values. You're saving the model from processing a mountain of unnecessary data on every single turn.
To put this into perspective, Anthropic's research reports that lazy loading can drive an 85% token reduction, leaving you with just 15% of the original token cost. That is absolutely massive for both your latency and your budget.
Next up, section 5, the agent as tool approach, diving into server-side inference and maximum control.
When you need pinpoint accuracy, you really have to stop relying on the client LLM to interpret your complex schemas. Enter server-side inference.
This uses an introspection tool to call a faster, external model like Amazon Nova 2 Lite to interpret instructions before the main call. So, imagine a teacher asks for text-aligned content for dividing. You use that smaller, faster model on your server to perfectly map the natural language to your exact filter values before the main search ever happens.
For the ultimate evolution, we look at V6 Agent as a Tool features. This exposes a single natural language endpoint to the client LLM. Your internal agent handles the taxonomy and search completely behind the scenes, using something like the Strands Agent's SDK. You get persistent memory across calls and, crucially, consistent behavior across all client models. The client LLM does almost no work because you own the reasoning entirely on your end.
Finally, Section 6, Trade-offs, Choosing Your Path, and Evaluating the Architectural Matrix.
Okay, let's take a step back because there is no single perfect silver bullet here. Every approach has a core trade-off. V2 rich descriptions, you pay a context bloat tax. V3's schema plus defaults requires upfront modeling effort to restructure things. V4 lazy loading introduces extra round trips and latency. V5 server-side inference brings in external inference costs. And V6 agent as tool definitely has the highest infrastructure cost. Choosing the right architecture depends entirely on your specific realities. You can't just pick one blindly. You have to consider your field count, your vocabulary stability, your strict latency budgets, and your need for cross-client consistency. You have to balance these forces based on the actual constraints of your own code bases.
Hopefully, this explainer gives you the framework to stop just hoping your LLM will magically figure it out and start actively designing context that practically guarantees success. So, I'll leave you with this. Before you write your next line of code, how will you redesign your MCP architecture to finally balance bloat and confusion?